All right, good morning, everybody. Welcome to day 2 of Micro. We've got an exciting lineup of keynotes, panels, and student-oriented competition and talks today. Well, we've got 3 breaks, as I'm showing you here on the slide. We also have the socializing aspect of the conference at GatherTown. So please, session chairs, do recommend the attendees to take offline questions in GatherTown. Everybody do take advantage of the ability to socialize in GatherTown, and our keynote speaker during the break hopefully will be in GatherTown as well too. So another quick reminder with regards to questions for the keynote. Please type in your questions into the Zoom question and answer. Please don't type it into the chat. If you would like to ask a live question, just type in Ask Live and we will promote you to a panelist and you can ask the question live. And for paper sessions, please again, type in your questions in the Zoom Q&A. Session shares, please do manage your time and try to make the question and answer session as lively as possible. With that, let me first introduce our keynote speaker today. It is with great pleasure that I introduce Anastasia Ailamaki. She is a professor of computer and communication sciences at EPFL in Switzerland, and is also the co-founder of Raw Labs, a Swiss company developing real-time analytics infrastructure for heterogeneous big data from multiple sources. She earned her PhD in computer science from the University of Wisconsin-Madison in 2000. She has received numerous awards, such as the 2019 ACM Sigmod Edgar F. Codd Innovations Award, the 2020 VLDB Women in Database Research Award. She has also received numerous Best Paper Awards, got the NSF Career Award as well. She's an ACM Fellow and IEEE Fellow, the laureate for the 2018 Prize in Computer Science. She's an elected member of the Swiss, Belgian, Greek, and Cypriot National Research Councils. She's a member of the Academia Europaea and World Economic Forum expert. With that, I hand it over to Anastasia. Please take over.
Okay, can you see my slides?
Yes.
Can you hear me?
Perfect.
Yes.
Perfect. Yeah, otherwise you wouldn't have answered. Okay, good. Every few years, we find ourselves in the database community having to reinvent the way we think. And this happens because a lot of factors affect in a very deep way the design of data management systems. It used to be the case that we had only transactions to handle, then we had queries, then we came to this day where we have hundreds of different kinds of workloads on hundreds of different data formats on very, very different and continuously evolving hardware. So today I'd like to talk to you about the work that we've been doing with my lab and most notably Periklis Chrysogelos, Onraza, and Panos Sioulas, 3 of our systems students in the lab. And this work is an attempt to move intelligence, to move the thinking process of how to do things from preparation time, from before we write code, to execution time, to the code, to the time that the database code actually runs. So this is what we call real-time intelligence or real-time specialization. And I'm going to focus on 2 major ones of the game changers that I mentioned. There are more, but for today, we're going to talk mostly about the hardware and the workloads. Heterogeneity is the biggest problem. Variability is the biggest problem. For hardware, the problem is that since when I started working on this topic, which is since the 90s, the hardware has been increasing in heterogeneity and has been severely underutilized by database workloads. So the one can maybe a bit too simplistically summarize the trade-off here that we encounter from the point of view of the data management software between portability and performance. When we write hardware conscious code, we're on this side where we get very good performance, but our ability to have portable code that we can run on different kinds of hardware goes down. And alternatively, when we don't pay attention to the microarchitectural characteristics and we just write hardware oblivious code, generic code, with keeping our mind to portability, we have the opposite effect. Now, the variability that's coming along with all the accelerators, and most notably, and what I'm going to be most talking about today, the GPUs, is giving us this hardware heterogeneity that accentuates the difference between portability and performance and accentuates this trade-off in a way that we can't just ignore it anymore. We have to find this sweet spot. And what really happens here is that database engines have long relied on hardware improvements to scale performance over time. So here you see a conceptual little cartoon which shows you different engines. They're blue lines, right? All the engines are blue lines. And depending on how hardware conscious the code will be, the blue line will be close to the optimal hardware performance as promised, as advertised or not. And the more the hardware evolves, say, for example, with the introduction of multi-cores and multi-threaded hardware, we get a better performance. The engines that specialize more, the engines that involve code, execute code that's close to the hardware, that observes the hardware characteristics, the cache characteristics, for example, or the levels of the memory hierarchy. All of these engines enjoy a higher performance improvement that I mentioned here, a specialization benefit, for lack of a better term. And the more conscious an engine is, the better, right? The more an engine that's less hardware conscious is more is less performant as hardware evolves. However, as the variability of the hardware is increased by the introduction of accelerators, and even more with large networks of servers running data management workloads, one sees very much this trade-off that we give up, the performance deteriorates much faster, and what we call the portability debt, in order to stay portable, in order to write software that will work on all sorts of hardware or on new hardware as well, we are going to pay a lot more portability debt in performance. And that doesn't stop. It will continue. And here's another very simple graph where we run on CPUs. In my talk, CPUs are going to be always in blue, either in a drawing or in a graph, and GPUs are going to be always in green. So we run a simple database workload. On the one side, it's join heavy, and on the other side is scan heavy. And don't worry too much if you don't know what these things mean, because I'm going to explain some of it in a minute. But join basically means that we involve two different tables and we bring them together. So it's kind of a more complex, if you will, operator. Scan is just scanning files. But it's also, these are two very, very common things. And you can see already that if you run it on CPUs, you get a different performance depending on what you run than if you run it on GPU only. And then you have the mix in the middle. Again, same thing. But if you ran on CPU and GPU at the same time, it's one of multiple experiments that we have done with workloads, you get a really good performance, but you have to do it well. You have to observe that there is heterogeneous hardware and specialize to each device for what it's good for. And that's where the problem starts, because this isn't obvious how to do, okay? We talk about analytics. Analytics essentially means that we run queries, and these queries, these questions on the data help us analyze the data into useful information. So this is one could call a typical query where we are looking for an aggregate for a sum of reading 4 tables and combining them all together. And I'm not writing the entire query code here, but this is a very, very simple query that has some restrictions in what information will be selected. And then on the information that survives, that satisfies the condition, we compute this aggregate, this sum. And that's all it takes. And this query is parsed, and then it's optimized by information from the bottom to the top. So you can imagine that your data, your raw data is here at the bottom, and this data is being scanned by the leaves of the tree. And then as the data is being scanned in a hopefully pipeline fashion, the other operators are run until the computation of aggregate, and the information flows from bottom to top. Okay, so that's good. And if we look a little closer into all of these plans, we will observe 3 important types of operations. The first type of operations is the scan, and the scans are sequential access heavy, right? You can think about it as reading full columns of data. And then you have this more complex, if you will, operators. You have joins and aggregations, or group bys in other plans that create random accesses. And then you have the rest of the operations, as the plans can be arbitrarily long, right? And these operators need to support connecting arbitrarily, introducing complex code, which we're going to get into in a minute. But basically here, one function calls another, and that other function calls another. And if you think about it at the lower level, the processor needs to support function pointer calls and virtual function calls, this kind of. So I call them very loosely here sequential heavy, random access heavy, and control heavy parts of the plan, just referring to what is the biggest problem in the code here in terms of performance. So an example of a random access heavy, a join, as we mentioned before, is this operation that we bring together two tables and based on some common columns, we produce the combined result of the tables. And this traditionally creates a very heavy flow. Traditional creates a heavy processing in the system, right? So a lot of people have tried to make to create join algorithms, to invent join algorithms that are not just very plain join algorithms, but they are optimized for the hardware. And we're going to go over one of them in a minute. Similarly, for control heavy operations that have a lot of context switching, then we have vector at a time execution models are proposed. Essentially, of the table from one operator to the other to facilitate the exchange, but also have good performance. We send vectors which match the size of a cache line. And then finally, to make sequential scan faster, while parallelization started to exploit NUMA locality and work stealing, not only to maximize the sequential access bandwidth, but also to maintain common data structure across all the workers working on the same thread. We reduce the need of final aggregation step and additional scans of intermediate data by using fast atomic operation. So these are some of the optimizations, a small subject of the optimizations. And here, if you dig a little further in these optimizations, like CPU optimized joins, vector at a time, the new atomics, you can see that these all rely on bona fide CPU characteristics. So they rely on high cache size to thread ratios or efficient inter-socket operations to implement the atomics. And it won't necessarily work on an accelerator. And to illustrate this, let me just show how a fast equi-join algorithm will work. So this is a very common, very fast equi-join algorithm. Equi-join means that I join table R with table S based on a common column. So say, for example, student ID. And the condition is an equality. And that's why it's called equi-join. It's the most common kind of join. And typically you have a short table, say a satellite table in old-fashioned star schemas, and then a fact table, say a very long table, and you do the join. And a very fast such equi-join is implemented by first scanning over the small table, building a hash table using some hash function, and then probing this hash table with the larger table. Okay, so that's called the hash join, and it's the most common, the fastest, and also the most researched kind of equi-join that we have. And Peter Bones and co-authors in VLDB 99 proposed a similar hash join, but that's optimized for CPUs. Essentially, what they do is that they for two tables, they partition based on the key attribute, the column that is going to be used for the join, and they partition using a hash function, and they partition both tables using the same hash function as opposed to partitioning only one table. And then they build hashed, and then they partition again and again and again until they reach on the left-hand side, on the table that's going to be built into a hash table, they reach cache size partitions. And then they build hash tables on these partitions. And the point is to not overflow the TLB, and that the resulting cache lines, they fit in the L1 and L2, the on-chip caches. And then they probe. So this is great, and this is a very fast algorithm, and it works much faster than the plain algorithm that doesn't pay attention to cache size. But it's a great example for CPU only, of a CPU only optimization, because on GPU you have exactly the opposite. You have low cache to thread ratio. The caches are both software and hardware managed, and then you have collaborate execution of threads. So while the GPUs have a very promising high memory bandwidth, this join is going to be inappropriate for their architecture, resulting in similar or worse performance to non-partition join algorithms that themselves suffer from random accesses. So we port the Radix join to the GPU architecture, essentially overcoming these assumptions that we have, which are invalidated on the GPU. And the way we do it at a very high level, this is a paper we published in ICD 2019, is to essentially, if we suppose we have the GPU scanning a relation to be partitioned, then consecutive GPU threads of the same multiprocessor are accessing consecutive memory locations. So we have one output buffer per partition. And then here, these buffers are shown with a capacity of 4. Of course, they're much, much bigger. And write locality is important. So the threads first partition the accessed batch of data in shared memory, and then the threads read the elements back. So now elements that belong to the same partition are clustered together, and there's locality on the thread writes. And then the next step is to find out where to write each element. So we do atomics for the write offset in each buffer. And some buffers overflow. So before the write, we allocate buffer space from a buffer pool accordingly, and we create chains. Only then we can flush the elements to the partitions. And this way, this is just one part of the algorithm. This is a single pass GPU table partitioning algorithm that stages the output in the Scratchpad and has the threads collaborate and complete a cache line together, multiple threads. And if we have a ton of results in the paper, but if you see the speed up is at least 3.5, a factor of 3.5 over the plain algorithm on GPU. Now, this is a very simple example to rebrand, essentially, of rebranding a commonly used CPU optimized join for GPUs. And similarly, what I want to talk about next is how we can, using the same thinking, but a bit higher in abstraction, think bigger and move to the interoperator, control-heavy environment where we encounter overheads generated by the requirement to chain operators together in a query plan. Now, these operations, why is this a problem? These operations generate indirect function calls that reduce code locality and break instruction prefetching because the target call address is a runtime value. An example is the very common call to the next operation. So in the volcano model, which is the model, a name for the model that we use to implement query plans, the operator at the top asks the operator at the bottom. Operators are these little circles, the filters. So the operator at the top asks for the next tuple, next tuple, next tuple. And this next is a virtual function overwritten by each operator. So the next in a join is different than the next in an aggregate or in a group by or in a scan. And thus the actual code location is unknown until runtime. So, and you know, that's why we use code generation finally to switch this overhead from a per call to a per query case by generating pointer value for the jump into the code. So to do this, we use code generation and code fusion. And code fusion goes one step further, merging the functions after we code generate. So let's see an example. This is another query. This is much simpler because the example is going to blow it up a bit to a more complex infrastructure that we create. And this is just a simple query. This is SQL that just takes a table and singles out a column and sums up the values on that column that correspond to qualifying values on this different column. So it reads two columns and it does a sum. So there is one scan for the table, then the filtering to weed out columns that don't qualify, and then the aggregate is the sum. So normally we would just run this using 3 snippets of code, each one corresponding to this. But we don't, if we do that, then it's going to be just a blind execution on a CPU and it will not really be accelerated. We can't run this on with the same code as we saw on the GPUs, for example, or other accelerators in the system. So what we do instead is that we recognize that in order to go and use accelerators and different hardware, different than CPUs anyway, what we need to do is 2 things. We need to have transformations of data so that they fit better the cache infrastructures of different devices, CPUs and GPUs in this example. So we need data transformation, data control, data flow, if you will, operators. And then we also need to be able to change the routing of the operations and execute them where they will be optimized. What I mean is that sometimes you want to start executing on a CPU and then move execution to a GPU because there the execution will be faster, like we saw for the join just now, or the other way around. But in order to do that, you need to be able to move the execution. You need to be able to pack or unpack the data and observe all these different particularities of the different devices. Finally, we need to be able to fork out different instantiations of the plan so that we can take advantage of the fact that we have multiple CPUs and multiple GPUs. So how can we take this little plan here and turn it into a plan that will be executed efficiently on a multi-CPU, multi-GPU infrastructure? This is another publication in VLDB 19. We call this head exchange. And at the high level, what we do is that we take this plan and we enrich it with additional operators, which we inject into the plan and create a new plan, and then execute that new plan. Okay, so these are operators like, for example, router, a segmenter, which divides a pipeline in two, and then router that routes this pipeline into two devices, memory move, CPU to GPU, unpack data or pack data on the other side, etc., etc. So the objective here is to show to you that this logical plan creates a heterogeneity-aware logical plan that's still a logical plan. This is not a physical plan. This is not ready to be executed yet. So multiple operators are going to now be combined to execute this one single query. So this is, and then from this plan, just in time, we execute what we call pipelines. Pipelines are essentially parts of the query plan, part of this new plan that can be executed in a pipeline fashion. Where this pipeline breaks and another pipeline starts can be because we have device crossing, for example, or can be because there is an operator that cannot be pipelined. For example, sum is an operator, this aggregate is an operator that needs to see its last line of input before it generates its first line of output. So that's where the pipeline breaks. So this is why you have a break here, because you cross over to devices and you have a break here. So this plan will start executing on two CPUs, and then at some point it will execute on this GPU, and then it will move back to the two CPUs. So once we have the pipelines, and these are executed just in time, then we're ready to do code generation. So as in traditional code generation, when an operator is called to generate code, it will call its child to do the same until we reach a pipeline breaker. So let's see this one pipeline here, how it will start generating the code and create placeholders for the code of its parent. And this is an operator that generates its own code. And this for loop, for example, that you see in the middle, it will call the filter to generate the if condition, and so on and so forth. This is the blue part here. So at the high level, what's important here is that every pipeline is code generated, but also we go one step further to do a code generation procedure to inject information about the target devices into the generated code and allow for more portable operators. So specifically, we optimize these different parts of the generated code for specific operators using the knowledge that we have of the target device. Consider, for example, this simplified case where we generate the target independent code in the left-hand side first, as I showed before, and then the next step is to inject the target specific info. For example, these two cases for the GPU, we have a worker is occupying the whole device, all available threads are assigned to it when the kernel is executed, whereas in the CPU, a worker is a single thread and routers are used to parallelize the execution. So when we, so this way we do this for every part of the general, for the generated code. We inject this, we call them mappings, so that we can better bind to the device. And then finally, the last thing is that for every different pipeline that's code generated, we run it by generating multiple instances, so we can expand to all the available units in the system. So this way, the control flow is decoupled from the data flow, and this is a very high level table that shows the idea. Essentially, you have the control flow for delegation, where things will happen, and then routing. And then you have the data flow, where we deal with transferring data as needed, and then we deal with granularity of data as needed by different memory infrastructures. And this way, we distribute the load to devices adaptively. So what I talked about is essentially three abstractions, right? We have these live units that are called queries, query plans. And these query plans are the point where the performance of the analytics is decided. So these abstractions that we use. What we do essentially is that we decouple the query plan into 3 dimensions when we execute in a heterogeneous hardware platform. The first dimension is the dimension that takes what we call the physical layer, takes the physical implementation of an operator, so a join operator, a hash join, for example, the physical implementation, which could be a Radix join, and creates one physical implementation per device. It's a physical implementation, but it's logical as far as the hardware is concerned, because the real mapping, the injection of the target specific traits into the code, the generated code, happens in real time, and that's the intra-device layer. And then finally, we recognize the fact that there might be different devices. So we inject operators, we inject parts of the query plan that take into account the available resources in the system, the accelerators, the CPUs, and they encapsulate essentially this heterogeneity by creating a query plan that can be executed on any device and do all of the instantiation and the pipelining in real time. So this is one side. And the reason why I think this is forward-looking is that this idea, this set of ideas here, along with the code generation and fusion infrastructure that we have available today, and the programming capabilities in GPUs and other accelerators, allow us to evolve query plans without reprogramming the entire data management infrastructure for any kind of accelerated hardware and platforms. And this is something that we can maintain and sustain in light of the future of different implicit and explicit parallelism opportunities that we get, including ALP that we have today. So I'd like in the rest of the time, I'd like to just talk a little bit about the workloads. And the issue here is that we have two parameters of the workloads that are changing in real time almost. And the one of them is the complexity, and the other one is uncertainty, the unpredictability. The complexity is that is essentially that workloads today cannot just be classified in queries and transactions. Unfortunately, we've been thinking in queries and transactions. We've been thinking in information that we generate all the time, say, for example, with bank transactions or supermarket transactions. And then this information sits somewhere. And when we need to run analytics or make important business decisions, then we have all the time in the world to go and look at that information. And it's okay if it's a little bit old, and it's okay if it's not necessarily the most up to date, but it still helps us make decisions. Unfortunately, this has changed quite a bit. And this is a picture of what I was just saying. The idea is that you have transactions and everything is happening here dynamically, and there are a lot of reads and a lot of writes, and they're short-lived, and they are executed at 24/7. And then you've got analytics that used to happen in a much less parallel, much less frequent rhythm. And then there was this, which is a whole industry of software, it's called ETL software, that takes periodically what happens from the transactions side and moves it over to the analytics side. And that makes it available for queries. Of course, as you all probably have heard, this is no longer the case and has not been the case actually for a few years now. People are working on queries at thousands of queries per at the time. So the OLAP and other kinds of workloads that run analytics are much more parallel than they used to be. OLTP, there's a lot of demand on OLTP. These workloads are now called many names. They used to be called compound workloads. Now they're called hybrid transactional analytical processing workloads, or HTAP. But what's important here to understand is that although the essence has not really changed, in the sense that we've got these task parallel transactions here, which are short-lived, they have very high data access locality. They are at the point like changing line items in a fact table, for example. And then you've got this data parallel or long-running queries, which are very heavy and scan large parts of the database. What we want is to have all of this run at the same time. So I want to draw your attention to another similar but different trade-off that we have on this side, and that's between data freshness and performance. Because now OLAP, OLAP means online application processing. Essentially, all these queries that we run cannot live with old data or even minute-old data. Think about for applications, for example, like recommending systems or fraud detection, or all of these systems need fresh data in order to make their decisions, okay? So this idea where we have these databases separately doesn't really work, and HTAP requires that the system works on the exact same database and the infrastructure collaborates to both keep data freshness, but also have a guaranteed high performance. Because if the execution is co-located in the same system on the same database, then of course you'll get all the fresh data, because the transactions will be updating the data in situ, and that's exactly the place where the queries will be looking at the data. But it will be slower because of interference. OLTP and OLAP workloads running on the same infrastructure, the same memory hierarchy, step one on the toe of the other in terms of performance. And then the other way, the other extreme here is when you have separated execution, it's much faster because there's no interference in the memory hierarchy or in the interconnect, but at the same time, you have a lot of, you don't necessarily have the data freshness that you need for the application. So what we want is real-time adaptive scheduling of the workloads of both the queries and the transactions, which specialize in real-time online with at the data freshness rates as required by the application. And that's important because here, and that's very related also to the first part of the talk, where I talked about hardware accelerated execution of app analytics, because we can really explore the different characteristics of the devices in order to be able to resolve this workload and find here again the sweet spot. So this cartoon shows you the extremes, right? So one side you have, on the one side you have the extreme that I showed before, where you have this extract transform load, where you have less data freshness, but independent execution, which allows you predictably fast execution of the workloads. On the other side, you have two systems both running on the same database and running both OLAP and OLTP engines, and all of this it gives you more data freshness but lower performance. So you can do actually, you don't have to have the extreme. So in the middle, we have two hybrid designs here, which either provide compute isolation and provide fresh data access through delta accesses, which is bottlenecked by interconnect bandwidth itself, or they can reassign OLTP resources to OLAP and provide processing local to the fresh data. So, so just starting from the second, very simply, if you think of transactions as task parallel workload, you can increase the efficiency of the hardware by assigning transactions to CPUs. And then you can do the same, increase the efficiency by assigning the queries to the GPUs, because GPUs are more parallel. So queries run mostly on combs, and that's a data parallel workload. So it's much faster, it's much more efficient if we run them on this on the GPU side. So the idea is to initially roughly separate the resources between a data parallel side. Archipelago is the name that we gave to this side, to every side in the paper. So running on a data parallel side and on a task parallel side. But what's interesting here is that while you run, you observe the relationship between performance and data freshness, and also between performance and data freshness and locality. And when needed, assign on demand resources from the task parallel archipelago into the data parallel side in order to collocate as needed the OLAP and the OLTP sides. And similarly, the problem, just going a bit deeper here on how this connection would happen, we could have OLTP generating fresh data on the CPU memory, and then OLAP needing to access a fresh data. But then on some machines, we would have an NVLink style interconnect, and on some other machines, we would have a much slower interconnect. And in our recent experiments, we show that no matter what you run, no matter how you do the assignment, and also no matter how fast your GPU infrastructure is, so how advanced, how expensive the hardware is, if you will, the only thing that matters when running HTAP on CPU, GPU infrastructures is the interconnect. What's going to make it or break it is the interconnect. So here we find that it's not enough to be able to lend resources from the OLTP, from the task parallel side to the data parallel side in order to run collocate as needed the two different kinds of workloads. What we really need to do is to observe the data freshness and performance trade-off in real time by polling essentially the performance, and then when needed to even to tune the scheduling of the tasks to the two sides, and even resorting to an ETL approach by doing smart snapshotting as needed in order to maintain a smooth flow of fresh data from main memory to OLAP. And this way, we can essentially use this real-time intelligence that I was talking about to revert to even an extreme when needed in order to maintain predictability in the workload. I want to just end here by saying that we have a very dark future ahead of us in terms of both workload and complexity, but also hardware heterogeneity. We find workloads, we see workloads that start from IoT, ML, generally computer science related fields to data pipelines from other domains such as medical research, mathematics, etc. And for some of these domains, we see work on manually integrating them on existing databases or even existing hardware infrastructures and building new specialized systems. But each of these options takes a lot of time. We have hundreds of different data management systems today out there, and they just need to be combined every time in an ad hoc way in order to serve even a relatively simple purpose. So all this time-consuming infrastructure building effort can be much better if we allow all these bindings with the infrastructure and the resources to happen late as opposed to earlier. So, so we need systems that learn the functionality that's available, learn about the resources that are available, and then move on to use them. And I talked a lot about within the same machine, but we have a new paper that's coming out soon that basically talks about scale out, because RDMA networks today look like a single machine. The connections between servers, the interconnects are just as fast or even sometimes faster than the GPU CPU interconnect. So we have interesting games here between capacity and throughput and interesting trade-offs. So we're now looking into how to kill two birds with one stone, keep up with technological changes and using the available power efficiently by using the accelerators, while at the same time providing more input to the accelerators and enable them to be used. So instead of building from ahead of time intelligence into the systems in order to use that intelligence in real time, intelligence needs to be built during execution, so real-time intelligence. And because both hardware and workloads, but also data, which I didn't really mention today, are increasing in heterogeneity more than anything else. And that's the most important part. And a solution, a system today is going to be only as efficient as its least adaptive component. So we should take every component of data management systems and we should put it into a more real-time learning perspective so that we can remove all the assumptions and move on. Thank you very much.
Thank you, Anastasia, for the very nice talk. Audience, please start typing in your questions in the question and answer box. We have the first question from John Kalamakianos. Great presentation. Can you comment on how increased heterogeneity by the integration of custom accelerators, possibly targeting selected OLAP or OLTP workloads, and reconfigurable IP like FPGAs can affect future work on runtime specialization of data analytic queries?
Okay, I made the mistake to open the chat, so I missed part of what you were saying. But let me read it again because I got it. Thank you very much. Can you comment on how increased heterogeneity via the integration of custom workload like FPGAs can affect future work on runtime specialization Yeah, so this is exactly what I was trying to, this is exactly the message that I was trying to convey here, right? Which is the reason why we think we should bite the bullet, if you allow me the expression, and do this work and try to, instead of pre-coding existing features, to get the system to detect them and use plugin style mappings to inject device-specific these mappings in a device-specific snippets into the code late, is exactly this, that we want to encourage heterogeneity and composability at the infrastructure level. Now, I mentioned also runtime specialization. The reason why we want it, okay, utilization is one thing, but we want it because it really affects the performance of the system. It really affects the data freshness as well. And interference, for example, in a memory hierarchy is a huge problem. And it's been written, I mean, there's many people who've written about it and have run experiments. And workload interference is something that's largely ignored, for example, by the hardware, right? So it would be really nice if we could have at the cache hierarchy, caches that can handle interference somehow and can at least give some hints when there's the types of misses that allude to interference, such as associativity or non-capacity misses, so to speak. So this is an example.
Any other questions while people are thinking? I was wondering, can you comment on the challenges of data orchestration? You've been looking at CPUs and GPUs, especially having a different memory hierarchy, and you're moving computation from in the heterogeneous system. What are the challenges there that you find? Is there any opportunity for specialization while doing the data movement? And how does scheduling come into play?
So this is exactly what we're doing in this work that I mentioned here. It's this data movement. That's exactly when we do the specialization, when we find that the data freshness is being, the performance is being compromised because we have to pull from main memory, say, through a slow interconnect. We switch and to an ETL style mode, but there you need a tool that allows you to do ETL in real time without affecting performance. And there we've written a paper in which we published in Sigmod last year, where we do snapshotting that's friendly to this. So it's a special kind of snapshots, essentially. So that's an example of this kind of specialization that you mentioned, if I understood correctly the question.
That makes sense. Any other questions?
I think there is one. You talked about the heterogeneity in the compute. Does the heterogeneity in memory technologies, e.g. DRAM versus NVM versus HBM, could also add to the complexity of database operations? That's by Arkaprava Vasu. Yes, and thank you very much for asking this question. NVM is a huge chapter where, I mean, in my team, we're just scratching the surface, but this is exactly the point that I was making on the very first slide, that heterogeneity, variability is gonna be a problem on everything, because if you have more data, you can care, but you can also not care, because you can ignore it and only use it when you need to. So there you only care about your working set. If you have more applications, you can also look at every application in some order or whatever and do something in the outside. But when heterogeneity hits, so when quantity hits, we're fine. When velocity hits, we're fine. When variability hits, when heterogeneity hits, we're losing our assumptions. And that's what is the most important problem here. Heterogeneity invalidates our assumptions. And that's why structures crumble. And that's why all of this, I find this so exciting because it generates work on every possible dimension. Storage is a huge dimension. We've been looking at cold storage. A few years back, we had a study on cold storage for analytics. And it's really important that we maintain these dimensions, but with the mindset that things have to happen in real time now. Otherwise, we'll keep building different systems for every different configuration. So there's another one. What hardware did you test on? Should I continue or?
There's another question in here. What do you think about accelerating network analytics on FPGA SmartNICs? What kind of workloads would you expect to perform better on an FPGA compared to a GPU?
That's a huge, I don't think I have a specific answer to that because I haven't really worked on FPGAs. Gustavo Alonso has worked a lot on FPGAs and databases. FPGAs are very different than GPUs, as everybody can appreciate, especially in this venue. But for me, dynamic workloads such as HTAP, I don't know how I would be able to implement them on FPGAs and still maintain this composability and real-time, device affinity as I do. We can do this, but I really haven't thought of that, so I don't want to venture a guess there.
We have a question from Eric Altman. How quickly are these very impressive techniques deployed in large industrial database installations?
Well, I was going to say not quickly at all, but very recently, there's been technologies that are very similar to these mushrooming left and right, not for hardware that I know of. What I know of in the industry are mostly CPU only or GPU only still, data management. But there's been quite a bit of embracing of real-time intelligence for variability of data formats. My startup, Raw Labs, has been doing this since a few years back, and also other people are doing it at different levels, late compilation. So people are embracing this. They adapt their architectures to do as much close to the machine late compilation as possible. What I'm trying to advocate here is a changed philosophy that first changes the way that we abstract and then builds a different system, builds a different philosophy from the ground up. This, I don't know that it has been implemented anywhere yet, but it's fairly new.
We have a question from the Huva platform. What hardware did you test on, and did you find anything that surprised you about different types of hardware? By Sylvia Losa.
Thank you. So the hardware that we tested on were different GPUs and CPUs that we have available, mostly Intel-based, NVIDIA-based. All of the we tried to buy all the latest and greatest from the microarchitectures that different types of recent GPUs and CPUs. So every couple of papers we adapt to the more recent models if we can get our hands on them. But yeah, but it's Intel and NVIDIA for the most part. We have a bit of IBM also in there, and but mostly Intel and NVIDIA.
Thank you, Anastasia, for the talk. That brings us to the top of the hour. I'll hand it over to Dimitri real quick. before we end this session?
I want to thank also Natasha for the great talk. That's a little token, Natasha, from us for delivering the keynote today. A little certificate of appreciation. Thanks a lot. We will email and we will mail it to you as well.
Thank you. This is lovely. Thank you very much.
Thank you.
Natasha,
We have a
if
break
you-
right now. Yeah, go ahead.
We have a break right now. If you have the time and the opportunity, please hop on to GatherTown. The link is in the Hova platform. And the rest of the audience, feel free to join the GatherTown platform to do some socializing. Thank you.
Thank you, Amar.